All right, so chapter 2 is really, the whole point of chapter 2 is to get us ready for doing proofs, where we are trying to prove something is true. And so usually what a proof does is it gives us a given statement, and then it says to prove this statement. And so we have to go from the given to the proving part and show how are we proving it. So we're going through really a reasoning and a logical argument in how we're trying to prove, what we're trying to prove. And if you can kind of think of it in terms of an algebra problem, like a solving equation problem. Let's say you have a big equation to solve. Perhaps you got variables on both sides of the equal sign. Maybe there's even a parenthesis in there and all of that. And so that equation is the given part. That's usually what we're given. At the beginning, you have to be given something. So you're given an equation. But usually what we have to do is we have to find the answer, right? What is the answer for x? Well, let's just say that they give you the equation, but they also give you the answer. And they say x equals 1. Well, what a proof is it's saying, okay, with this equation, prove that x equals 1. Okay, we know x equals 1, but how do we prove that? Well, you would prove it by showing all your work, by doing all the steps, and by justifying each step, in fact. Not just showing all the steps, but also explaining your steps as you go through. So you would do the distributive property, and then you would explain, I did the distributive property. You'd actually write that down. Or you added 3 to both sides. You'd actually explain, I'm adding 3, or basically it'd be like the addition property of equality. That's what I just did. And so you have a statement, which is actually like showing your work, and then you have the reasons on the other side, which is actually just explaining what each step is that you're doing. And so once you go from the given part of that equation and go each step down to where x equals 1, now you've proved it. And that's really what a proof is it's that. You're given something and you got to get all the in-between part to get to the part where you proved it. And so to do that, we start off not with proofs. That does come later in this chapter, but we start off with understanding how to reason an argument, how to make a reasonable argument. And we start with that, with these conditional statements in 2.1. So that's what this is all about. 2.1 is talking about conditional statements, just understanding how to make something that's a logical statement, true, false kind of thing. And that's what we're going to look at here. Exploration number 1, A through D. All you have to do here is you're going to have you read through these. So read through each one, A through D. This is on page 33. There are your notes. Just read through each one and just answer whether that's true or false. Is it a true statement or is it a false statement? And then we'll go over that. It says justify your answer, which is kind of explain your answer. You can try to do that if you can figure out how to explain it. But at least put true or false, and then we'll go over it together. Okay, so let's go ahead and look at these. So letter A. If yesterday was Wednesday, then today is Thursday. Is that true or false? Yeah, that would be true. In fact, I'll just show you all these right here. Yeah, true. Thursday always follows Wednesday. So that's true. B says if an angle is acute, then it has a measure of 30 degrees. Now, you might at first think that's true because, yeah, a 30-degree angle is acute. But the way they said this, by saying that if an angle is acute, well, there's a whole lot of angles that are acute, right? Not just a 30-degree angle. And so that's why this is false, because we wouldn't conclude if the angle is acute, then it's just automatically 30 degrees. It could be 50 degrees or something else that's acute. So that's why that one's false. 30 degrees is only one example of an acute angle, it says there. C, if a month has 30 days, then it is June. So again, that's kind of a similar one as B, where, yeah, June does have 30 days, but it's not the only month that has 30 days. So, another month that has 30 days is September. So we could have, we could be in September, which we are right now. So a month has 30 days. We could be in September. So that's why it says false. June's only one of the months that has 30 days. Obviously, we wouldn't be in October. We know there's an October 31st, Halloween. That's obvious. We're not in that month, but we could be in a different month that has 30 days. D, if an even number is not divisible by 2, then 9 is a perfect cube. Now that's a challenging one right there because we already know, we can just see from the very first statement here, even numbers are always divisible by 2. That's what makes them even, really, right? So just that right there itself is false. And then 9 is a perfect cube. Well, we know 9 is not a perfect cube. It's a perfect square, but it's not a perfect cube. And so we know that's false too. So you might have been thinking, okay, you're going to say false on this one. But because both the first part and the second part were both false, then the whole statement actually is true. It's kind of a weird situation. It says true on this one because we know all even numbers are divisible by 2. 9 is not a perfect cube. So because both hypothesis and conclusion are false, this conditional statement is true. All right, let's go on to exploration number 2. We're going to also look at true and false for that. You're given a, this is on the next page, page 34. You're given a little coordinate plane here on this one. 4 points are up here. You're going to have to kind of see, and I wouldn't necessarily draw the picture of these things because it's going to be a little confusing. I would just kind of look at them like A says triangle ABC, and then B says triangle BDC. Those are 2 different triangles. So we see what triangle you're looking at there by each one. And then down here, the last 2 say quadrilateral ABCD. So they're using the whole thing there. So you're having basically 3 different shapes to look at. So you're just going to read these statements here based on these points and those triangles or quadrilaterals. Is the statement true or false? Again, it talks about justifying your answer, which is a key part here because that's really the explaining part. You do need to explain yourself when we're talking about proofs eventually. So try to figure out how would you explain why you're saying true or why you're saying false. All right, so go ahead and answer those, and then we'll go over those again together. Okay, so here we go. Letter A. So we're looking at triangle ABC, and really it just says it's a right triangle. So is ABC a right triangle? I'm going to go ahead and just pull these all out here so we can see that. So we would say yes, it's true. It is a right triangle. But really the justification here is very important. It's just as important as saying that getting the true or false right. We would be saying that, well, AB, that segment right there, that's vertical, and BC is horizontal, and we should always know that a vertical line and a horizontal line are always perpendicular to each other, and perpendicular lines are always right angles. They always intersect at a right angle, and so that's what we would say to justify or explain why that is definitely a right triangle. Letter B, it says this triangle right here is an equilateral triangle. And if you remember from maybe before what equilateral means, it means that all the sides are the same. So each side is equal. And we can see just by right here, this we can count how long BC is. We can see that's 8 units long. And we can look at B to D or even D to C and see those are definitely not going to be 8 units long. Now you can definitely check that with the distance formula, right? We can use the distance formula with those 2 points to see exactly what the distance is from B to D or D to C, and it's going to be less than 8. Just by looking at it, you can see that that looks longer than that does. So this would be false. It just says that BC segment is longer than the other 2 sides. Just by looking at it, you should be able to kind of see that. C says that same triangle BDC, is isosceles. It's an isosceles triangle, and if you remember from what that word means, isosceles, now we're going to see some things here that we haven't learned yet in our geometry. You may have seen them before, like in junior high, they're supposed to go over some geometry sections, and you might have seen some of this there. But isosceles means that 2 sides of a triangle are the same. And so this one is true because BD does equal DC. You can kind of see that because if you go from D here, you go down 5 and then left 4 units to B, down 5 and right 4 units to C. It's exactly the same distance for each way from where the D is here in the middle. And so they are both going to be equal. You can again check that with the distance formula. D right here now talks about the quadrilateral. So we have a quadrilateral ABCD right through there. It says it's a trapezoid. Well, now we need to remember, what does a trapezoid mean? Well, a trapezoid is a quadrilateral, but it has two parallel sides, just a parallel sides. So one pair of parallel sides, I should say, where the other sides don't have to be parallel, but one of them does. And you could see, well, AD and BC are both horizontal lines, so those are going to be parallel. These two are not parallel. You know, AB is vertical, D to C is definitely not vertical. So that would make a trapezoid then, yes. Yes, this is true, it is a trapezoid. E says that it's a parallelogram, that quadrilateral, same one, is a parallelogram. We need to remember, what does a parallelogram mean? Parallelogram means that both pairs of opposite sides are parallel. So not only just that AD and BC are parallel, but these two have to be parallel as well. So obviously we said that AB was horizontal, was a vertical line. This is not a vertical line. So those are not parallel. So that means that definitely that's false. It's not a parallelogram. It is a trapezoid because it has one pair of parallel sides, but it's not a parallelogram because it doesn't have two pairs of parallel sides. So that's what it kind of says down here. AB is vertical, CD is not, so it's not they're not parallel. So that means it's not a parallelogram. All right, let's take a look at exploration number 3. Same thing, just answering true or false, but try to justify your answer as well. Try to think through how you might explain whether it's true or false. So that's over here. So read through these, answer true or false, and see if you can think about how to explain it. All right, let's take a look at these guys now, A through E. So if you have triangle ADC is a right triangle, so it tells you that it's a right triangle, then the Pythagorean theorem is valid for that triangle. So when can we use Pythagorean theorem? When it's a right triangle. So yes, that would be true. So that's true because Pythagorean theorem is valid for all right triangles. That's when we would use the Pythagorean theorem, is for specifically a right triangle. And then B says if angle A and angle B are complementary. We learned that word last chapter. Complementary means you're going to add them up to equal 90, right? 90 degrees. But this one says if angle A and angle B are complementary, then the sum of their measures is 180. Well, that's not right. So that's false, right? Because we know complementary equals 90. C, it says if figure ABCD is a quadrilateral, then the sum of its angle measures is 180. Now that one you might not have known. Maybe you remember that from somewhere before. But the measure of the four-sided figure, quadrilateral, the inside angle measures are always going to add up to equal 360, not 180. A triangle is 180, but a quadrilateral is 360. So again, that C is false, because it says that the sum of the angle measures of a quadrilateral is always 360. And D says if points A, B, C are collinear, then they lie on the same line. Well, we learned that word last chapter as well, collinear. And again, that means exactly what this says, that they are points that lie on the same line, so yes. And our reasoning is just the fact that that's the definition of collinear, is that they lie on the same line. So we're using our definition to justify our answer there. And that's a lot of times what happens when you're doing proofs. If it's something where you can just use a definition, this is just the definition of this. You know, that could be an explanation of what you're doing, a reason why. E says that this line AB and line BC intersect at a point. So if they intersect at a point, it's like X marks the spot. You have a line and another line, X marks the spot where they intersect. Then they form two pairs of vertical angles. Remember, vertical angles are the ones that are congruent, and that's true because it's going to form like an X. And that's really what kind of vertical angles look like, is they do form an X. It says every pair of intersecting lines forms two pairs of opposite rays and therefore two pairs of vertical angles. That's more the technical explanation, but you could have explained it a little more loosely than that. All right, so that's the explorations, and what we were really kind of getting used to in these three explorations is what a conditional statement is. It is a statement that has an if and a then part. And so that's what we go on to next, is looking at the vocabulary for this. And you may want to pull out a highlighter to highlight through the core concepts, because that's really the key stuff there, is the vocabulary. That's what you're going to be tested on, is vocabulary, not so much problems so much as much as you are going to be tested on the vocabulary and just understanding the words here as we go through. So start off with this core concept, conditional statement. What is that? Well, right there, you can see that a conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. That's what you'd write down for just what, you highlight that part for conditional statement. That's what we've been seeing this entire time through those three explorations, is all of those were conditional statements. If this, then this. And I'm going to kind of focus on that very first one that we did about the days. And the very first one we said was, if yesterday was Wednesday, then today is Thursday. So right there, underneath this, let's go ahead and write that. So let's go ahead and write underneath here, conditional statements always in if-then form. If this, then this. If the hypothesis, that's the if part, then the conclusion. The conclusion is the then part. And let's go ahead and write that one down here. We're going to use that one throughout. So it said, if yesterday was Wednesday, and then comma, so that's the hypothesis right there. The if part, then today is Thursday. And that's the conclusion part, the then part. And we're going to use this same statement each time. We're going to rewrite it a little bit differently each time based on what these next things are going to be telling us to do here. So the next one is negation. It says that what basically negation here is, negation of a statement is the opposite of the original statement. That's what negation is. It's the opposite of the original statement. Up here I didn't highlight this part, but the if part is the hypothesis, the then part is the conclusion. So just make sure you realize that you need to know what a hypothesis and conclusion are. So basically it's doing this. Now it does give you these symbols, and you may see the P and the Q. You don't have to worry about the P and the Q symbols. I'm not going to test you on the symbolization of these things. And really you're just tested on the understanding the vocabulary of it. But basically in words, if P then Q, words for negation is just not P. So P was the hypothesis. So if we wanted to say, okay, not P from this statement, if yesterday was Wednesday, we would say if yesterday was not, I'll make that capital right there, not Wednesday. That's the negation part. That's what negation does. It just inserts the word not into your hypothesis or conclusion, depending on where you want to put it. But basically we negated the hypothesis right there. We inserted the word not. That's negation. It's the opposite of the statement. What's the opposite of yesterday being Wednesday? Yesterday not being Wednesday. It just puts the word not in there. Alright, so let's move on to the next ones. Still going to use that same illustration. The next ones are, and again, don't worry about the symbols, but the next one you're going to look at is called the converse. Now you may want to write this word up here right above it, because I always think of the converse as reverse. Really is the reverse of the if and the then. It's the reverse of the hypothesis and the conclusion. And so the definition here says the converse, basically, it's of a condition that exchanges the hypothesis and conclusion. And you might want to write down that it switches the hypothesis and the conclusion. So that's why normally it's going to say P then Q, like if P then Q. Well, it switched it now, and now it's if Q then P. So if the conclusion, then the hypothesis. So if we're going to use that same statement, let's write it here for this one. We would say if Now remember the conclusion part was today being Thursday, right? Okay, that's what we wrote down. So if today is Thursday, that was the conclusion part, but now we're putting it up front, comma, then, now we're talking about the yesterday being Wednesday. Then yesterday was Wednesday. Was Wednesday. I'll just put WED for Wednesday. Shorten that up a little bit. So if today is Thursday, then yesterday was Wednesday. That's the converse of our original statement. Okay? That's just switching the hypothesis and conclusion. Next one says inverse. So what does an inverse do? The inverse of a conditional statement, this is what it does. It negates both the hypothesis and conclusion. So it's going to insert the word not into both the hypothesis and the conclusion. So if again we go from our original statement that we had, which said if yesterday was Wednesday, but we're going to insert the word not here. So if yesterday was not, right there, I'll put the word not there, was not Wednesday, I'll use abbreviation for Wednesday, comma, then today is not, right there, putting the not word in the conclusion as well, Thursday. So if yesterday was not Wednesday, then today is not Thursday. So you're negating both the hypothesis and the conclusion, and that's called the inverse. Okay? That's what the inverse is called, when you negate both hypothesis and the conclusion. Now notice where the word not goes. It goes after the verb, right? Your verb in this statement is was. If yesterday was not Wednesday, was the verb. Your verb here is. Today is, so it's going to be is not. So the not goes always after your verb, okay, when you're going to negate something. Still have one more about this. So we've talked about negation, and now converse, inverse, and there is one more next, as you can see it there in your notes. It's called contrapositive. Contrapositive. Let's see what that's going to do. The contrapositive of the conditional statement says first write the converse, which we know is the reverse, the switching part, then negate both hypothesis and conclusion, which is the inverse part. So basically the contrapositive is both converse and inverse. You might want to put that up here near that, or you can say it's both converse and inverse in the same thing. So if we were to write that here for this one, and don't have a lot of space, I'm going to put it down here. So if we were going to write that, first we would switch the statement. So we're going to have to talk about today being Thursday first, but we're also going to negate that. So we're going to say if today is not, right, we're going to put the word not in there, that statement. If today is not Thursday, comma, then yesterday, S-T-E-R, day, I'm trouble spelling the yesterday, then yesterday was not, again negating that section as well, was not Wednesday. So that's the contrapositive, because we did both the converse, where we switched it, and we also did the inverse, which we negated both the hypothesis and conclusion. We inserted the word not into both of those. That's called contrapositive when it does both, where you're going to do the converse and you're also going to do the negating both hypothesis and conclusion. So that now is everything we could do to a conditional statement. So lots we can do to a conditional statement, the if-then form of a statement. This next one, actually before we get to the next one, we talk about equivalent statements. Let's go and just highlight that one too. That's a pretty easy one to understand. It just means basically when two statements are both true or both false, that's the equivalent statements there. That's what equivalent statements means, is when two statements are both true or both false. They're called equivalent statements. Equivalent just means equal to. Those statements are equal to each other then, if they're both true or they're both false. So that should be an easy one to kind of pick out and see that one as a definition, like if you were to try to match definitions up with their terms. Now this next one is now a different form than a conditional statement. The conditional is always if-then. If, hypothesis, comma, then conclusion. It's like if P, then Q. That was the symbols we talked about. But this one is going to use this if and only if. So a biconditional statement is a statement that contains the phrase if and only if. So biconditional statement is always going to say if and only if. That's how you know it's called a biconditional. If it has that phrase in your statement, you know it's a biconditional statement. If and only if. Now we can change an if-then form to a biconditional form. So here's how we would do that. Let's go back again. Think of our original statement. Remember the original statement was if yesterday was Wednesday, then today is Thursday. Let's make that now a biconditional statement. I would write it like this. I wouldn't use if. I wouldn't start it with if. Okay, biconditional statement does not start with if. It just is going to say that yesterday. Starts with the word yesterday here. Oops, I can't even spell yesterday. Putting the D too early. So yesterday, there we go. Yesterday was Wednesday. See, it just uses the statement part, doesn't put the if, just says yesterday was Wednesday. Yesterday was Wednesday, and now what we're going to use is this if and only if part. That's going to go between the hypothesis and conclusion. So yesterday was Wednesday if and only if, we can kind of, I'll underline that part right there. That's the key part there. If and only if today is Thursday. That's our biconditional statement. So we changed our if-then statement, our conditional one, to biconditional just by doing that. Just by taking away the if-then kind of form and inserting if and only if in between your hypothesis and conclusion. So this still, right here is your hypothesis. I'll underline this in red. That is the hypothesis right there. And this over here is your conclusion still. It's just now you stick this if and only if between those two. Okay? Okay, so one more definition that you need to know from this 2.1, and you want to go back to page 35 where the vocab is, because this one you're not going to highlight, you're actually going to have to write it down. And that would be where perpendicular lines. So you have perpendicular lines right here. So what are perpendicular lines? They are lines that intersect to form a right angle. And we talked about that earlier. But that's what the definition will say there. Or I should say two lines, not just lines, but two lines intersecting to form a right angle. Two lines that intersect to form a right angle. Those are perpendicular lines. That's all you need to write down for that page really on 35, because everything else we highlighted. That's in the core concepts. And these last couple, the truth tables, truth values, you don't have to worry about those. We're not going to cover those. That's not going to be in anything you're going to need to know. So that's all the vocabulary in just 2.1. I know there was quite a bit. And that's stuff you are going to need to remember. They're going to be on a quiz coming up at the end of Chapter 2. So now take a look at your extra practice next. So that is on page 38. There are 6 problems in the extra practice, and I'm going to have you try to do these on your own. So work through, you can start with 1 through 3. Work through those. It just says to write the conditional statement in if-then form. So it gives you a statement, you just need to put it in the if-then form. That's for at least 1 and 2. And then number 3 wants you to do all the stuff that we just did to that one statement about yesterday being Wednesday and today being Thursday. You're going to do that for what it gives you there, for that conditional statement that it gives you. So that's right here on extra practice. Start with 1 through 3, and then go on to 4 through 6. All right, so let's go through 1 through 3, just see what we have here. So all we need to do in this one is just change this into a if-then statement form. So this is what I was kind of talking about at the beginning, where you're given the equation and here is you're given the answer. And so in a proof, this is kind of what the given is and this is what the prove part is. So here's your hypothesis is always going to be your given, and your conclusion is always going to be your proving part. So if this, then this. That's all you had to do there for that one. So basically, I'll show you these here. So if x equals -1, then that's true. Okay, so if, in fact, that was backwards in kind of what I was talking about, but basically you would say, okay, well, if x equals -1, then 13x minus 5 is going to equal -18, because if you plug in -1 here, that would equal -18. So that's why we're going to change that to an if and then. So it may be backwards than what you wrote down. That's okay. You can just go and switch it or show that it's supposed to be switched. In this one, the sum of the measures of interior angles of a triangle is 180 degrees. So here's what you could say. If a polygon is a triangle, because we have a triangle and a triangle is a polygon, if a polygon is a triangle, then the sum of the measures of its interior angles is 180 degrees. So you're changing it into where you have some kind of a hypothesis and a conclusion. So if your hypothesis is that this shape, this figure, is a triangle, then we can conclude that the sum of the measures of its interior angles is going to be 180. Because this is going to be a true statement here they're giving us, same thing like we have here. So if we know that this is x equals -1, if we know that, then we can say that this is going to equal here -18. Now this one's a little different. We're going to want to be given this statement here. It says let P be this. So here's your hypothesis, and let Q, which would be your conclusion, be this. First of all, it says to write a conditional statement. So this is going to be a little bit easier because it tells you here's a hypothesis, here's your conclusion. So if this, so if quadrilateral ABC is a rectangle, comma, then this, then the sum of the angle measures is 360. And so that's what it's saying there. The conditional statement is that is true. Because that is true, we know that quadrilateral, the interior angles, are always going to equal 360 when we add them up. The next thing it says is to write the converse. So that would just switch it. So now you're going to write the converse of that. So the converse would then put this part first. So if the sum of the angle measures is 360, that's what it says. If the sum of the angle measures is 360, then this part, the quadrilateral ABC, is a rectangle. And it does ask us whether it's true or false here. So write the conditional statement, then decide whether each statement is true or false. So that first one was true, but the second one, when we switch it, notice it changes it to it's a false statement. Why is it false when it changes the hypothesis and conclusion? Well, because the sum of the angle measures is 360 for all quadrilaterals, not just a rectangle. Rectangle is only one of the kind of quadrilaterals we can see. So that's why, just by knowing this, that it's the sum of the angle measures is 360, to definitively say that, well, that shape's a rectangle, we can't say that. It could be a rectangle, but it also could be other ones, like some kind of other quadrilateral where it's not a rectangle. Next one says inverse. So that's where we're going to be negating each of these. So we're going to say that the quadrilateral is not. Remember, you're going to put the word not after the verb. So it's not a rectangle. It is not 360. And so that's where you're seeing this here. If a quadrilateral ABC is not a rectangle, then the sum of the angle measures is not 360. And when we do that, it also changes it to false. So just the fact that your quadrilateral is not a rectangle doesn't negate the fact that the sum of the angle measures is still going to be 360. So that's where you can use the word negate. It doesn't negate. It doesn't make it false. It doesn't mean that it's not going to be 360. And really, negate is the word not. It doesn't mean that it's not this. So if it's not a rectangle, it doesn't mean that it's not 360. It still is 360 just for the fact that it's a quadrilateral. And then the contrapositive, that's where we're going to switch both of them. So we're going to be switching them and negating them. So Basically now the negation of this first, if the sum of the angle measures is not 360, then the quadrilateral is not a rectangle. Notice that one's true, because if the sum of the angle measures is not 360, then it couldn't be a rectangle, because a rectangle is a quadrilateral. The sum of the angle measures in a rectangle is always 360. So that would then make this true. Yeah, if it's not 360, then it's definitely not a rectangle. It'd be some other kind of shape. All right, let's go on to 4 through 6. Go ahead and do those ones. So we're looking here at 4 through 6. It says decide whether the statement about the diagram is true. So there's your diagram. Explain your answer using definitions you've learned. So do 4 through 6, and then we'll talk about those. All right, so hopefully you've done 4 through 6 by now, and you just want to see if your answers are correct. And again, you're seeing, is it true or is it false? So LM bisects JK. So LM, we're looking at this one right here. It bisects JK, and that we'd say is true because of the definition that we know of a segment bisectors. It makes these two congruent. And those congruent marks show that that's definitely a bisector on that one, number 4. So true, the bisector symbol in the diagram indicates that segment JR is congruent to RK. That's these two right here. So that's definitely meaning that's a bisector, a segment bisector. Angle JRP and angle PRL are complementary, which means they'll be adding up to 90. Is that true? So JRP, JR and P, this one right here, and PRL. So PRL, this one right here. So are they adding up to 90? Well, we're going to say false on that one. It may look like it's 90, but we have to say false because there's no right angle symbol right here. It doesn't show us a right angle symbol with a little box there. So because that symbol is not in the diagram, we can't say and indicate that that is a right angle. So that one is false. It may look like it's complementary, but we can't, actually prove the fact that it's complementary through the diagram. Number 6, angle MRQ is congruent to angle PRL. So MRQ, this one right here, is that one congruent to PRL? And that one is true because they are vertical angles, because you can see the opposite rays. So P to Q are opposite rays, and M to L here, these are opposite rays as well, going from R. So the intersection point is R, and you have these opposite rays. So that's what they're basically saying down here. You can say that kind of the way I did, or you can just kind of write this down if you want to. But show some kind of explanation for that one. All right, so that concludes 2.1. We're going to move on to 2.2 next, and I'll see you on that lesson.